Okay, so this is the lesson for Thursday, April 9th. We're going to be reviewing what we did the last time we were together. We looked at interval bounds and we looked at Descartes' rule of signs to give us pieces of information about polynomials. So I want you to put this in your notes, put this polynomial in your notes, and we're going to put this together. All right. Let's revisit the Descartes' rule of signs, shall we? I usually go ahead and find p of negative x or f of negative x before I make my sign chart. So understanding that all the even powers will keep the same sign and the odd powers will go positive, it looks like this. Okay. So let's organize our table like so. We'll put negative roots, we'll put positive roots, and then we'll put imaginary. And then we have a totals column. The totals column will be the fundamental theorem of algebra, which says that the highest power is the total number of zeros. So not knowing how many columns I'll need, I'll just fill a bunch of these. So the 4 is the highest power. I like how there's no sign changes in f of x. That limits me to 0 positive real roots. There's no other alternative. You can't have, we know this will never cross the x-axis to the right of the origin. How many sign changes do we see in f of negative x? Let's see, 1, no, 1, no, hold on. So 1, 2, 3, 4. Am I doing that right? I think so. So that means we have either 4, 2, or 0 negative real roots. So we have either 4, 2, or 0, which means the imaginary would look like this. It has to add the 4 in each of the columns. And so this last column is not needed.
Yeah.
Wait, what's that?
Never mind. Okay, I see it.
What were you confused on? I'm curious. Oh, because there are no sign changes in f of x. Since there's no sign changes, that means there's 0 positive real roots. Since there's 4 sign changes in f of negative x, that means there could be 4, 2, or 0. I can subtract 2 until I get to a negative number. Chris? Yeah. How do I get which 2? All right, so I take the number of sign changes and I subtract 2. And then I subtract 2 again until I can't subtract 2 anymore. Is that okay? Keep subtracting 2, and that gives me possible cases. All right, go ahead, Anna.
Wait, so you can never get past 0. Once you hit 0.
Right, I can't have a negative number.
Okay.
So don't go to negative values. Okay, now, we talked yesterday about doing interval bounds. So when they do not give you a starting point, the example you have in your notes right now, it said show that 2 was an upper bound and negative 3 is a lower bound. If they don't give you the starting points, then you have to start at 1 and negative. 0 can never be a lower or upper bound. It always starts at 1 or negative 1. So let's do this. Let's put a 1 here, and we're going to synthetic divide and see what comes up. So let's see, 1. No, what we're doing is we're looking for an upper bound. Okay, so bring the 1 down. 4, let's see, 4, 8, 8, 11, and then 11, 12. So this is indicative of an upper bound because all of my numbers in my quotient and my remainder are positive. So what I can say now is that 1 is an upper bound. And we should have had a hint at that with Descartes' rule of signs. The Descartes' rule of signs says that there are no positive real roots. So I can never find an x-intercept to the right of the origin. So it would make sense that 1 is an upper bound. I will never find a 0 greater than 1. All right, so now we're going to search for a lower bound. I'm going to start with negative 1. And what I'm looking for is alternating signs in my quotient and remainder. So let's see here. So 1. All right, so I can stop because I don't have alternating signs in my quotient. And you're looking at me like we haven't done this before. Let me show you, reference the notes what we did right here. So you wrote this in your notes yesterday. We talked about upper bounds being indicative of the positive values and the lower bound is alternating signs. All right. So what I'm looking for is that alternating sign in my quotient and my remainder. So let's try -2. -2. Let's see, 1, 3, 4, 3, 1. That's not going to do it. So -2 is not a lower bound. Let's try -3.
So you just keep going down the
I just keep going down the integral path. I never have fractions. It's always integers. Go ahead.
Is there like a faster way to do this, or is this? Really
Nope, this is what we got to do. Go ahead, Julia.
Okay, so for the upper bound, like if you put in 2, would the signs be alternating?
No, it would be all positive. 2 is an upper bound, but it's not the best upper bound.
But I thought 1 was the upper bound.
Right. So look what happens when I do 2. When I do 2, I will get nothing but positive answers.
Yeah.
Do you believe me? Here, I'll go back up here and do it.
Oh, I don't.
So when I do 2, I'll get 1, 2, 5, 10, 14, 28. Look at that. Nothing but positive answers. So 2 is an upper bound, but it's not the best upper bound.
So 1 is the best?
1 is the best upper bound.
How do you know? Yeah, how do you know if it's the best?
Well, because the upper bound, let's see, -1. We'll look at -1 here. So -1, let's change. So 1, 2, -1, 2, -2, 1. Oh, we found a better one. Here's a better one.
What?
Because look at my sign change. Look at my signs. My signs are nothing but positive, 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 and 0 could be anything. So -1 is a better upper bound than 1.
But I thought you said 1 was the best upper bound.
We're going to correct that.
I'm so confused. Okay, so can I like try to reiterate it? to you?
Sure, go ahead.
All right, so the best upper bound is when all of it is positive and there's a remainder of 0. Is that correct?
When the best upper bound is found, when it's the lowest number that you can find nothing but positive values in your quotient and your remainder.
Okay,
Okay.
okay.
So I think we tried -2, didn't we?
Yeah, we're gonna do that.
And well, we're going to do it again. So let's try -2. Let's see. All right. I'm just going to use this part of the board. So let's try -2. So 1, -2, 1, 2. But I'm getting all positive here, aren't I?
No,
And then, oh, I'm going to get negative there, aren't I? All right, because I'll get -4. So this is neither an upper or lower bound because it doesn't have all positive numbers, nor does it have alternating signs. So now we can say that -1 is your best upper bound. We will not have a root greater than -1. Okay. So now we're looking for a lower bound. So we tried -3, right? So -3, 1, -3. 0 could be any sign. We could make that negative, so that's fine. So this is 0, 4, that's positive. This is -12, so that's -9. And then look, I have a positive 27, which is 28. So we do have positive, negative, positive, negative, positive. So -3 is our best lower bound.
is 0 always negative?
It could be positive. 0 could be the sign you need.
So it's either or.
It's either or.
All right, cool.
Yep. So let's wrap that up. Best upper bound is -1. Best lower bound is 3. -3. So I will not have zeros above -1, and I will not have zeros below -3.
We just keep doing what? Shooting the number, there's no difficult or like one.
Yeah, you're looking for the signs, and you just keep going by 100 times. Okay? Now, I did graph this. Hopefully this makes sense now. So here we go. So here's a graph of it. Can you see where the zeros are? Where's the zeros? It looks like it's at -2. Looks like it bounces right off -2. So let's see if that matches up what we came up. We said that there would be no root above -1. Is that what we found? We said there would be no zero below -3. We're okay. That matches. And hopefully it matches one of these scenarios. So the scenario that we have here is the middle guy. It turns out we have 2 negative real roots. We have a bouncer, don't we? So that means we have 2 roots at -2, and then that means we'll have 2 imaginary roots. All right. The thing about the integral lower bounds is you're never going to be looking at 0, and you can. I think if you look at your book. Right, B has to be greater than 0 and A has to be less than 0. All right, so let's go forward. Okay, we're not going to do that. Not going to do that. Not going to do that. Here we go. So here's where we're going to make our money. So we need to be able to write this as a product of linear factors. All right, let's do this a couple different ways. This smells like it's factorable to you. Does it smell factorable to you? I think it is. I think we can factor this by grouping. So this is doable by a technique we learned back in Algebra 1b. We can take an x squared out and get x plus 2, and we can take a -3 out and get x plus 2. Then we can take the x plus 2 out, and we're left with x squared minus 3. Now, it does say linear factors, so I have to find the zeros to x squared minus 3. So let's do that. So I'm going to write x squared minus 3 is 0. So x equals positive negative radical 3. So the linear factors will be x plus 2, x minus radical 3, and x plus radical 3. And that's the factor theorem. It says if I can find the zeros, then I can find the linear factor. So if the 0 is radical 3, then x minus radical 3 is its linear factor. Okay. Now so before I pull that graph out, can we sketch a graph of it by hand? You bet we can. What are the x-intercepts? The x-intercepts are -2, 1.7, -1.7. So the zeros are -2. So this is -2. This will be about 1.7, and this will be -1.7. The in behavior is odd positive, so it does this. Are there any bouncers?
No.
No, because there's no even multiplicities, so it's got to run through each one like that. And I bet we're pretty gosh darn close. Holy smokes. Wait, well,
Bounce.
hold on. It doesn't bounce. Can I show you? And this is why these are kind of flawed. Because when there will be a calculator portion of the test and a non-calculator portion. On the calculator portion, the TI-84s are a little bit flawed because it doesn't actually bounce, even though it does. And I'll show you. That's why we like to rely on the algebra versus this. All right, so here's the graph I just showed you. I don't think you're watching anything if you're a senior, but when I zoom in, look what happens. it goes through -2 and then back down through -1.7. So it's not a bouncer.
So if you recommend that we should zoom in at times?
Yeah, I mean, if you're questionable whether or not it's a bouncer, you might want to zoom in, just like I just did. All right. So the 84s can be a little bit misleading if you're not careful with them. And welcome back, seniors. All right. I hope you're enjoying your milk and cookies, guys. Need some more cookies, Brian? Okay, they're back in the back. Okay, so look at this one. This is the same type of problem, but it's not factorable, right? There's no technique to factor this. So now we have some tools to think about how we could do this. When we factored it, we were able to find the zeros. So that's what we're going to do first. We'll first find the zeros and then write the linear factors. How are we going to find the zeros? Louder, Anna.
I don't think it's right.
Huh?
Synthetic division.
We're going to use synthetic division. We're also going to use the rational root theorem. We're also going to use Descartes' rule of sums and maybe a little bit of integral boundness. So all those tools on our tool belt are going to get us through this. It's very tempting to pull that graph over and look for the zeros, but we can do this without. Okay, I'll say it again because there's a portion of the test that's non-calculator that you're going to have to go through this. So, using the rational root theorem, I can find possible rational zeros. What are they? 1, 2, 4, and the positive negative of those. It's a lucky day when your leading coefficient's 1, because you just take factors of the last number, and those are your possible rational zeros. How many real positive zeros do I have?
3.
I'm looking. Wait, hold on.
No.
3 is the total number of roots. I just want what Descartes says. What does Descartes say?
1.
How many sign changes?
Oh, 2.
So 2 or 0. How many real negative zeros?
1, 2.
So let's see. Be careful. F of negative x is negative x to the third plus 2x minus or plus 4. So just one sign change. So let's use that. We know that there is exactly one negative real zero. And we're going to hope that it's rational. We're going to hope that it comes from that rational list. Might be your lucky day. It could be irrational. It could be like negative square root of 3, which would not show up on our list. But we're going to hope and pray that it's going to be -1. And it might be. We're lucky. But notice, a lot of kids will start with 1 and 2 and 4, but we're not guaranteed a positive real zero. We're guaranteed that it's 2 or 0, but we're guaranteed 1 negative. So let's start with -1. So we're going to use that placeholder. We struck out, right? So -1 doesn't work. Let's try -2. Oh, lucky day. Lucky day. Look at that. So -2 is a 0. The remainder is 0. And since we have a cubic, our quotient is quadratic, and we have 1x squared minus x plus 2. I check to see if it's factorable, and if it's not factorable, I'm going to use the quadratic formula. All right? Is it factorable?
Yeah.
Factors of 2 that add to -2?
No.
Not factorable. We could complete the square. You want to complete the square? No, we're going to use the quadratic formula. So all together now, x equals -b plus or minus square root of -2 squared minus 4 times 1 times 2 all over 2 times a and 1.
I can't Back and forth.
Let's see, so 4, what's the discriminant here? Let's see, 4. Oh, it's going to be negative, isn't it? So it's going to be negative 4 over.
Wait, how'd you get 4?
Oh, sorry, 2. Yeah.
Okay.
So that's going to be, it's going to be negative. All right. So then, what do we have? We have 2 plus or minus 2I over 2, 1 plus or minus I. So we have 1 negative real 0 and 2 imaginary zeros. So how many x-intercepts will we see when I pull that graph out? Let's go and look at the graph to make sure we're right. Look at that. We have 1 intercept at negative 2 and no other x-intercepts, which would mean the 2 remaining zeros have to be imaginary, right? Because if you're real, the real zeros are x-intercepts. Your imaginary zeros don't show up on the graph. So can I write this in complete factored form? You bet I can. Let me show you how that's done. So the zeros are negative 2, 1 plus I, 1 minus I, which means the factored form would be x minus negative 2, x minus 1 plus I, and x minus 1 minus I. So that's the factored form. You can use the imaginary zeros in your factors. It looks weird, but if we did multiply that all out, we'd have the beginning polynomial. We're not going to do that.
So your answer is?
So the question was find the complete factorization, and there it is at the very bottom. That's the factored form. That's the linear factors composed of your real zeros and imaginary zeros.
Where's the x minus all that?
Where'd it come from? It comes from the factor theorem. The factor theorem says that if c is a 0, then x minus c is a factor. So 1 plus I is a 0, then x minus that is a factor.
Okay.
Is that too small? Do I need to make that larger, you say? How about that? Okay, all right. Ready? Next one. I told you it's going to take all hour. All right. Let's get that. Okay, so here's a good question. Continuing with that notion, if we have the zeros, can we write the polynomial? Let's do that in one grand display of this. So we know this. We know that we have a degree 3 polynomial with integer coefficients, and the zeros are 1/2 and 3 minus I. There's a problem here. If it's degree 3, that means we have 3 zeros. Do you remember writing down yesterday that imaginary zeros come in pairs? So we know this. If we know that 3 minus I is a 0, then 3 plus I is a 0 as well. That's given to us. It's the free. Imaginary zeros come in conjugate pairs. So there they are. There's the 3 zeros. Now we have to write linear factors. All right? And so we're going to go backwards. Let's do this. X equals 1/2. X equals 3 minus I. And then x equals 3 plus I. I do this because of this rational 0. I want to clear out that fraction and get 2x equals 1. And so 2x minus 1 equals 0. So 2x minus 1 is the actual linear factor. So here I get, well, it's probably quicker to just jump into your factor form. So 2x minus 1 is a linear factor. And then x minus 3 minus I. And then x minus 3 plus I. So I'm taking each of the imaginary zeros and just subtracting them from x. Some of you might say, but Mr. Smith, can't you do x minus 1/2? Can I take this 0 and write x minus 1/2? You could, but that will not give me integer coefficients. If I want integer coefficients, I'd want to clear out the fractions first. Let's oil the imaginary section first. That's a little bit hairy than what we like. So let's see, x squared. The outer product is minus x times 3 plus I. The inner product is minus x times 3 minus I. Look at the last. The last is going to be negative times a negative is a positive. Okay. Julie, need more orange juice?
Yeah.
Okay, to the back.
All right.
Help yourself.
Thanks, Mr. Smith. You're the best.
Yep. Glad you could come today. All right, let's clean this up a little bit. We should have some eyes canceling here. Oh, shoot, this is plus I, isn't it?
Yeah.
Yep. So this is 9 minus 3i plus 3i minus I squared. Oh, gravy, look at that. That's going to be, hopefully things clean up. I think things will. These go away. The xi's go away. That's kind of handy. And then, so what are we left? We're left with 2x minus 1. And we have an x squared. I see a minus 6x. I see, oh, this I squared is negative 1. So it's going to be plus 1, right? So plus 10. Now we just have your standard Algebra 1b problem. All right, so what do we get? 2x to the third minus 12x squared plus 20x. And then minus x squared plus 6x plus 10. Oh, jolly day. Look at that. We got it. So that cubic polynomial has those 3 zeros.
I'm crying.
I knew this before I went to college. Am I crazy? Like you guys.
Mr. Smith, how did you know you wanted to be a math teacher?
You're going to catch us on the recording on this slide.
Oh, I mean, you can pause it if you want. Like, I don't care.
No, we've got too much to do
Wait,
here.
I have a question.
Okay.
Where did you get the minus x squared plus?
All right. So let's see. We distribute the minus 1. So when you take through the minus 1, it's a minus x squared plus 6x and then minus 10. Is that okay?
Okay.
Let's get back to the fun stuff. This is kind of the you know, it feels like you're get stuck in mud on this. So here we go. Are you ready? No, let's not do. Got that written down? Let's do this. Okay, here we go. So putting it all together again. We're going to use the Cart's rule signs. We're going to use the upper and lower bounds. We're going to use synthetic division, and we're going to use the rational root theorem to figure out the zeros and the product of linear factors. Notice I don't even have the graph ready to pull out. That's not going to be a crutch right now. Okay, we're not going to use the graphing calculator here. Although think how easy that would be if we could.
Why are you lovely?
So if I could graph this, what would I be looking for? You don't know, though. You'd be looking for the x-intercepts. The x-intercepts are the zeros. But there's ways around it without having the technology. Let's go back to the, I guess we can go back to the 1700s and pretend like we're Rene Descartes doing this for the first time.
Did you learn with the graphing calculator? Do they have?
I don't remember.
Nothing.
Rene Descartes did this in the 1700s without a graphing calculator.
I bet it's my brain.
All right, here we go. So what would Janae Descartes say? Let's do this. Positive. Well, good thought. That's another tool we have. It doesn't factor by grouping. All right, because we take an x squared out, we're left with 2x minus 3, and there's nothing to take out from the 6. So Descartes would say positive real roots. How many are there? 1, 2. 2 or 0. How many negative real zeros? See, that's going to be a negative. So it'd be 0. That's going to be a positive.
No, it's
Good Lord. So that's, was it positive to begin with?
No,
No, it was a
it's
negative.
negative.
So that's 0, 0. Hold on, that's going to be,
That's gonna be positive.
it's going to be positive. So 1. So just 1, right?
Yeah.
Yes. All right, so let's go back to my original. So this is minus and then positive. That's what you got in your notes, right?
Yeah.
So 2x to the third minus. All right, so that's good news. That's just like the other one we had. 2 or 0 or 1 negative. So that's kind of nice. The rational root theorem will say possible rational zeros. These are our candidates for rational zeros. I'm going to take factors of 6 over factors of 2. So 1, 2, 3, 6 divided by 1 and 2. So dividing everything by 1, I get positive negative 1, positive negative 2, positive negative 3, positive negative 6. And dividing by 2 will give me some repeats. I think we had this same exact answer yesterday, but we get positive negative 1/2, and then positive negative 3/2. So we've narrowed down a list of infinite number of possibilities to 12. Kind of a nice deal. We also know that it's going to be likely that one of those negatives, do one of those negative numbers have to be a 0? The answer is no. Because even though we guaranteed one negative real, it could be it could be not imaginary but irrational, like negative square root of 3. But more than likely, it's going to be one of these nice integers. So let's try negative 1. All right. So 2. Let me make sure my signs are right. I think so. So 2, negative 2, negative 5. 5. Oh, holy cow. Oh, this is such a great day. Oh, no, it's not. Oh, yes, it's not, is it?
No, it's not.
Oh, it's just Jesus. Are my signs right here? Was this the original problem
Yeah.
too? Okay. So negative 1's not it. Let's try negative 2. Oh, here it is. 3. Thank you. All right. So here's a good question. Negative 2 is a 0. Is it a lower bound?
Yeah.
Yes. Why is it a lower bound?
Because it's positive and negative.
Yeah, we have positive, positive, and the 0 could be a negative. So a 0 could be a bound. That's fine. It can work. So we know there are no zeros left of negative 2, which doesn't really add anything new because we already knew that. We knew that there was one negative real 0, and once we found it, there's not anything left of that. And look what we have left. We have a quadratic left, 2x squared minus 7x plus 1. I do think that's factorable. You can mark it if you'd like, but I'm just going to do the old trial and error. Not here today. Okay. So let's see, minus and a minus ought to do it. I think that's right. Negative x, yep. So we just found 2 factors and 1 0. What do they want? They want the zeros and the product. So let's do that. The zeros are negative 2. This factor gives me a 1/2, and this factor gives me a 3. And the factors will be x plus 2, 2x minus 1, and then x minus 3.
And that's your answer.
Yep, they want the zeros. My 3 zeros are right here. They're all rational. And they want the linear factors, which is in the green. Not one time did I get a graphing calculator. That's pretty powerful. It's like we're doing math in the 1700s. Pretty great. Why not do it today? All right, here's another one. Why is this problem different? How is it different? Think about the fundamental theorem of algebra. Hmm? There's 5 terms. What about the degree? Yes, degree 4. So the degree of difficulty, if you will, is raised up a little bit. See what I did there? So looking for, here we're looking for 3 zeros and then 4 zeros right there. All right. What shall we do first? I'm going to let you guys walk me through this.
Because it changes.
Okay, sign changes. So Descartes is sitting there looking at sign changes, and the positive real roots, how many sign changes? None. So we now know that there's no place where it crosses the x-axis to the right of the order. There are no positive real zeros. That's pretty nice. That eliminates from our rational root theorem all the positive values. Okay? How about negative real? Well, you almost, let's go ahead and write it out. It's going to be x to the 4th minus, this will be plus, this will be minus, this will be plus. So 1. So there's 4 sign changes, which means we have either 4, 2, or 0. That doesn't help us a whole lot, but more the positive aspect is. Then let's, look at the rational root theorem. This is oh man, did you guys see this? The rational, hold on, the possible rational roots. How many are there? This is where I take factors of the last number divided by factors of the first number. They're just positive, negative 1. And Descartes' rule of sign will eliminate the positive 1. So the only possible rational root that we have is negative 1. If negative, so is negative 1 guaranteed to work? No, it's not. This is where we take factors of the last number divided by factors of the first number. That's the rational root. All right, so we're not going to do 1 because of Descartes' rule of signs. So we're going to do negative 1 and cross our fingers. That feels good. That feels really good. Look at that.
Like now I have to do the
Right?
You guys are based on your own. So Shayna recognized that these are all positive values. So they're, and I hope that makes sense. We've already said that this is the only x-intercept. This is the only real 0. So, okay. But look what the problem is now. What we're left with then is x to the 3rd plus x squared plus 2x. I cannot use the cubic formula.
We have to do it again.
We gotta do it again.
Oh, we can't do that.
Oh, that sounded like frustration to me. I am feeling excited.
Oh, wait. Yeah, can you do grouping?
Well, all right, let's take out a. Let's try it. Let's take an x squared out and get x plus 2.
Wait, no.
Oh, shucky darn! I do not. I don't have the same linear binomial. No. But good thought. I'm glad you guys are thinking things that I should be. So factoring by grouping doesn't work. So what are they going to do now? It's not a quadratic.
Oh, do the opposite.
Do the opposite.
I don't know. I like as in like, woo, start the process.
Yes.
Like,
Rinse,
like negative.
lather, repeat. So the cards. Okay, so these properties still hold for what's left. So I still know there's no positive real roots. But look at the rational root theorem. The rational root theorem says that my possible rational roots are 1 and 1 divided by 1. But we know that 1 doesn't work. It might be that -1 would work again. And that's the only thing that I can try. Because the rational root theorem says that the only possible roots are 1 and -1. So we could have a double root, a bouncer. -1 could be a bouncer. Let's see. And it is. So -1 is a double root. The double zero, which means the factor would be x plus 1 to the second power. We're left with the quadratic. Does this quadratic factor? No, so what are we going to do? Quadratic formula. And all together now, x equals -1 plus or minus square root of 1 squared minus 4 times 1, 1, 1, all over 2 times 1. All right. So this cleans up rather nicely. -1 plus or minus, that looks like radical 3 over 2. Oh, it is I. Yep. So we're going to take an I out. So 2 imaginary zeros. So putting this all together, because remember what they asked for? They asked for all the zeros and the product of linear factors. So now we're ready to do this. Let's list out the zeros. The zeros, and you can do this one of two ways. You can write -1, or you can write -1 double rooted. Or how you usually see that. We have -1 plus radical 3i all over 2, and -1 minus radical 3i all over 2. So as a product of linear factors, it would look like this. So we're going to be subtracting each of these. So I can just write that as x minus 1 squared. And you're going to just subtract this whole thing right here. There we go. Is that too small down there? Probably. Dang it, Julie, you are, it's like you're 2 steps ahead of me.
Julia, why did you say
That same thought went through my head. Because I've got one more. We've got 10 minutes. I'm going to give you 5 minutes to do this by yourself.
5 minutes? They were taking a
And then I'll use the last 5 minutes to do it together. Okay? But I do want you to start this and see if you get through the whole process. Did you see that not one time did I grab a graphic calculator?
Yeah.
That's pretty bold. I like that. All right, so here we go. So this is your chance to show understanding. You're going to try this. I'm going to pause the video and engage. If you're still watching this video, I want you to come to me and say, Mr. Smith, I watched that whole video, and I heard you say quadratic formulas. There's no